David Smith here with another flipped classroom math lesson. 3 tips before we start. First, you can adjust the playback speed if that helps you get through the video. Second, you can pause the video at any point to take notes or work the examples. Third, you can turn on the captions and read my words go by on the screen. Today's lesson covers exponential functions and the transformations thereof. So let's take a look. An exponential function is a function that has a variable in the exponent position. Now, if you recall the first 2 lessons in this chapter, we dealt with laws of exponents and then we dealt with exponential equations. So those are your basic tools you're going to need to move on in this chapter. So let's take a look at the form of an exponential function. You're going to have some constant times some base to a power. There's our x. You could have plus or minus some number in the exponent, so that's what the h is standing for. And then finally you have a constant outside. Now, in a minute here, we're going to talk about all these things, what they do to the function, because they transform the basic exponential function. So, check this out. Here is perhaps the simplest function. F of x equals 2 to the x. This is known as the doubling function, because each time you add 1 to x, you're doubling the last number, okay? So let's take a look at the graph. Check this out. It goes through the point 0, 1. In fact, most functions, or all functions, if there's no constant out here, it's going to go through 0, 1, because x to the 0 power, 2 to the 0 power is going to be 1. So we go through the point 0, 1. That's when x is 0. And then when x is 1, we have 2 to the 1, which is 2. So that gives us this point, 1, 2. Now we're doubling, right? 1, 2. Now we're going to double again. When x is 2, that's 2 to the 2, which is 4. So the point 2, 4, and so on. So this is growing exponentially. Now, a word about exponential functions and exponential growth. Technically, this is what's required for you to say it's exponential growth. Commonly, quadratic equations, f of x equals x squared, people talk about that as growing exponentially. Technically, this is quadratic growth, not exponential growth, because the variable is not in the exponent. So that's just a little side piece of information for you. Okay, let's take a look at all these parameters that we have, and we'll discuss them. We'll get these into your notes so you have your reference, and then we'll look at a bunch of graphs. So, first off, with these functions, they always have a horizontal asymptote. So there's a number which they approach as close as they can, but they never get to. That's an asymptote. In an exponential function, it's related to this c, which is a vertical translation. So this is going to move the whole function up or down by some amount, c, and that c is the horizontal asymptote. Okay, so this here is what moves that function up and down, and we can get our horizontal asymptote right from c. Okay, moving along. The y-intercept. These functions always cross the y-axis. They don't always cross the x, but they do cross the y-axis. So the y-intercept, you can get it right out of the equation. It's 0, because that's x when it crosses the y-axis. It's going to be k plus c. So whatever this number is added to whatever the c number is. And that's going to give you your y-intercept right there. Now the a is the most complicated term in here. And that's, if you remember the formula for a quadratic equation, a is also the most complicated term. It does a lot of things for the function. In fact, the same thing with this. So if a is bigger than 1, that means the function is going to increase, and you're going to have exponential growth. If a is between 0 and 1, that means you're going to decrease. It's going to come down from the left and decrease to the right. So that would be exponential decay. Now here's the twisty thing with that, is that if your exponent is negative, then it switches this, and it switches the graph to being below the x-axis. So that's an added complexity, and we'll take a look at the graph in a minute on that. Finally, h shifts the function to the left or to the right, and that's up here in the exponent. And so that's going to move the function this way or that way. So pretty much we move this graph around just like we move any graph around, and these are all the parameters that tell us how to do that. Okay, one more task before we get into the graphs. I've got two functions. F of x is 3 to the x plus 2, and I've got g of x, which is 5 times 0.2 to the x minus 3. Now what I want you to do is pause the video and enter the information in this chart for the horizontal asymptote for each function, for the y-intercept for each function, and then finally state whether the function is increasing or decreasing. So pause the video, do your best to fill that graph in, and then come back. Let's see how you did here. Okay, check it out. The horizontal asymptote, that's just c. So y equals c. Here's my 2 for this function, so the horizontal asymptote is 2. In this one, the horizontal asymptote is -3. So there we go. We've got that. Now, next one, y-intercept. That's going to be 0. Remember, at the y-intercept, the x is just always 0. And it's going to be k plus c. Now, this is 3. You might think, there's no k. Why isn't it 2? Well, there is a 1 there. We could write 1 times 3 to the x plus 2. So there's a 1, even though we don't write it. So that's why it's 0, 3. Now this one, we have 0 again, and we have 5 minus 3, and that gives us 0, 2. Okay? So that takes care of the y-intercept for these two functions. Finally, let's state whether they're increasing or decreasing. Now check this one out. A is the 3, and that's bigger than 1, so this is increasing or growth. Okay, so remember these keywords growth and decay, because you're going to get some word problems that are going to talk about exponential growth and exponential decay. Okay, so for this one, the A is 0.2, so that's between 0 and 1, which means we're decreasing, and we're calling this one decay. Now, really quickly, what I'd like you to do is use this information and make a quick sketch of each of these two graphs. Okay, remember that keyword was sketch. So we don't need a whole lot of information. We just need to use the information we have in our table. So this one is increasing. And I know that the horizontal asymptote is 2, so the whole graph is above the y-axis. So all I did is I just made my axes. I drew my increasing curve like that. Didn't pay a whole lot of attention to exactly where it should or shouldn't be. And I marked my asymptote, or I'm sorry, my y-intercept at 0, 3. And then I marked my asymptote at y equals 2. So that's that first graph. Now the second graph, I know I'm decreasing, that's decay, and I also know my asymptote is at -3. So really quickly, I sketched my xy axes, and then I drew my decreasing curve, and I made sure it went below the x-axis so I could draw the asymptote at y equals -3. And then I also recognized that my y-intercept is positive, it's at 0, 2. So it would be a mistake to come in like this. It has to come in and cross the y-axis at the point 0, 2. So quick sketches based on this. This would be a really good sort of intro to medium level difficulty problem. Okay, here we are in Desmos, and I'm going to do a little bit of playing around with graphs in Desmos so we can quickly compare what some of the parameters do for us as we graph. Let's pop over to that screen. Okay, so here I am in Desmos, and I've got my basic doubling function. If you look over here on the left side where my cursor is swirling around, you can see that I'm graphing y equals 2 to the x. This is my favorite, simplest exponential function. It's just the doubling. So I'm going to go ahead and add another function right in here. We're going to compare graphs. So let's do 2 to the x. Now you can see it's done what it's expected. This now is the horizontal asymptote. So we've moved it up from the x-axis all the way up to the line y equals 2. And I can graph that line just by going in here and doing y equals 2. And you can see very much that that green line, the y equals 2, is our horizontal asymptote for this function. So let's go ahead and close that out. Now let's just play with this while we're playing with the horizontal asymptote. Let's do a -2 on there. You can see now the blue line is 2 below. So we haven't changed the shape of this function at all. We've just moved it down. It looks like it might be curving a little differently because the lines are getting closer together up here, but that's
just because the function's moved. It's not because the shape is different. The c term, the constant out at the end, at the right of our function, only moves it up and down and determines the horizontal. Let's take a look at something else here. Let's do 0.5. Back this up, there's 0.5. Now check this out. I'm going to go ahead and turn off the 2 to the x. 0.5 to the x is like the opposite of the doubling function, halving function, halving function. So you can see this now is decreasing instead of increasing. Remember, 2 to the x, let's turn that back on. 2 to the x is an increasing function because 2 is greater than 1, so the function's going to grow. 0.5, this function over here on the left, that's between 0 and 1, so that's a decreasing function. And in fact, you can see that very clearly on the graph. It's decreasing. Notice how there's no c term, so the horizontal asymptote is the x-axis. But if I do like a +3 here, you can see my function just popped up 3. So that's how that one works. Now, let's play around just a little bit more. I'm going to do my 2 to the x function here. But I'm going to go ahead and put a negative in my exponent. And this is kind of an interesting switch. Watch what happens. Whoops, got to get it over there. There's my negative. So it just turned that function around. And it actually, now here's the interesting thing. This is the same as 1/2 to the x, as 2 to the negative x is 1 over 2x. So we can add that function in there and you'll see that it's the same. So I'm just putting in y equals 0.5 to the x. And you can see that that purple line is right on top of the blue line. So these two are equivalent functions. They're both decreasing. So this is that thing I put on the board. The exponent is negative. It reverses the function. So again, if I take the negative out, there is the blue function, which is our doubling function. It goes up as we would expect. So that's kind of like an interesting thing. There are equivalent functions for your exponential function. Now let's multiply the base. Let's do a 5 times 2 to the x. And I'm going to go ahead and turn on my 2 to the x again. There. You can see the 5 is causing this thing to rise a whole lot more quickly. We still have an asymptote on the x-axis at y equals 0, but now our y-intercept is at the point 0.05. And remember, we're adding k, which is 5. That's the term in front of the exponential term, plus c. In this case, there's no c term. We don't have, we're not shifting the function up. Plus 2 on there. Now our intercept is at point 0.07 because that's the 5 plus 2. That gave us that. So let's that out. I'm going to take the 5 out. One more thing. Do x minus 4. Whoops, no, this is where I get into trouble with Desmos. Let's do x minus 4 like that. So check it out. This has shifted our function 4 to the right. So this is like the vertex form of a quadratic equation. The minus sign inside the parentheses on the x squared term actually moves the graph in the opposite direction. So minus means you move in a positive direction to the right. And if we change that to a plus 4, then it moves the graph to the negative direction. This is only a horizontal translation. The graph looks maybe like it's got a different curve, but that's just because it's a curve. It is the same exact shape. So I think that covers everything. What I encourage you to do is when you use your when you do your homework or when you're working through exercises or you're watching a video, use your calculator or pop onto Desmos and play around with these graphs. The calculator or Desmos are a really good tool to get a feel for what the graphs are like. You might get questions that give you a function and say, quickly sketch this function. And that's going to help you do that.
Okay, let's finish up with an IB word problem. And I've got to tell you, when you see functions, exponential functions, you're going to tend to get word problems. We had this with our trigonometry unit, and we're going to have this with the exponential unit. So here's our situation. A boat's value over time is given by the following function. This is the English symbol for pounds. So the value is given in pounds, and X is the number of years. So I've defined that over here for you there. And what it is it's 20,000 times 0.85 to the X. Now this equation tells you something about what's happening to the boat's value. So think about that for a sec. Is it increasing in value or decreasing in value? If you said decreasing, you're right. Here's our A. This is the base that's being raised to the power. That's between 0 and 1. So the boat's value is decreasing every year. Now, if you understand your percents and all that, you're going to realize that 0.85 means that each year it's worth 85% of what it was worth the previous year. So that's just good to know so that when you get to your answer, you can kind of evaluate it for reasonableness. Okay, so here's your first prompt. What is the value when the boat is brand new? So if you understand how this equation works, you really don't have to do anything. You can just say what it is. However, I would like you to do the calculation and come back. So the key critical thinking step to realize is that when the boat is new, it's at year 0. It's new. It has not been out as a boat that's been bought. So we just put in 0 for X. Now anything to the 0 power is 1. So this term goes to 1. So the boat's value when it's new is just 20,000 pounds. Okay, so now do the value after 3 years. Pause the video, crunch the numbers, and come back. Okay, so straightforward plug-in step. I'm just using my formula, but I'm going to do 3. I'm going to find out what 3 gives us. So I put my 3 in my exponent's position, got out my calculator, did my calculation. The boat after 3 years is worth $12,282. So a side note, boats and cars and things like that that get used up are not good investments. Check it out. For 3 years, it costs you almost $8,000 to have a boat. That's not the maintenance, it's not the gas, it's not the repairs, that's all extra. It costs about $7,700 just to have a boat. So you got to think about that. It's not an investment. Last question. When will the boat be worth half of what it was when it's new? So pause the video, write a nice little equation, and solve it. Okay, if you couldn't come up with that equation, let me do that for you, and then you can solve. So here's the starting value. Here's our exponential stuff. We don't know the X, but we want to know when it's worth half. So it starts at 20, ends up at 10,000. So now, pause the video and do your math. Okay, so I need to divide my 20,000 away so I can just have my exponential term here. So I just divided 10,000 by 20,000. That's 0.5. So I have 0.5 equals 0.85 to the X. Now, there's no algebraic way to solve for a variable, an exponent in the variable, a variable in the exponent. You can't do that. So what we use for that is logs. And this is just like using the trig functions on your calculator. We can't do sine of 52 on paper. We need a calculator to do that. Same thing with solving for variables and exponents. So this is just log 0.85 of 0.5. So you put that in the calculator and it tells you that the power that would make this thing true is 4.27. So it takes about 4¼ years for the boat to be worth half of what it was when it was new. So again, 4 years, 3 months cost $10,000 to have a boat. Now, if you want a boat, great, have a boat, but don't think of it as a good investment. Now that you've watched the video, jot down a few extra notes or questions for our next class. You can also re-watch portions of the video that you didn't understand the first time. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.